Right, so welcome back everyone. The next talk today is by Misha Belkin from Ohio State, who will remind us that we are at the Simons Institute.
Thank you, Philip, for the introduction. Yeah, I would need to thank, where is Natty? I would need to thank you for giving my talk. Well, but I have some other points too. Okay, so first I wanted to call it the power and limits of kernel, but then I decided to call it the limits and power of kernels. So this is joint work with my student Yuan Ma, and he did a lot of great work on this, and also with Chao Liu, and recently with my colleague Raif Basili. Okay, so well, let me just go very quickly through it. Well, we know machine learning and AI is very important nowadays. It's kind of pretty much everywhere, modern sort of modern electricity, as they say. And it's based on things which look like this. This is Google Net, and this has about 10 million parameters, and you can see it's rather complicated. So it would be nice to sort of, from a scientific point of view, to understand some aspects of this. How does it work? What works about it? And what can we understand? You know, there is a little bit of sort of fog of war going on because there is a lot of excitement, but it's kind of figure out what's crucial. All right, so what I would like to have is I would like to have a model for modern ML. By modern ML, I mean large-scale supervised learning. And only that, which is competitive on these large-scale data sets, at least on some of them. It's analytically tractable and convex, okay? Pretty reasonable. Okay, so here is, I would like, so this is probably, I will not be able to talk about everything, but basically first I would like to talk about what are the limits of kernels, what are kernels and what are their limits. And I kind of would like to argue that kernel setting already gives us a model like that it actually reflects a lot of properties of neural networks, at least empirically observed. And second, I would like to sort of how to make kernels competitive on large data. What is the power of kernels? Yeah?
So in your model for modern ML, does neural nets and deep learning have no place there because they're not convex?
No, they serve as a model for themselves, but I would like something which is convex and tractable, right? I mean, certainly they work, we know that, but I would like something which we can sort of understand theoretically, and ideally which would work just as well. But that may or may not be possible, at least. Well, on some problems, I think it's clearly possible. Yeah? Second, why is SGD so effective? And this actually relates to overfitting, which is kind of a very weird thing which is going on, I think. And once we sort of address these computational issues of kernels, we see the modern behavior of kernels. SGD is very effective for kernels. They do show overfitting, and the results are very similar to what people have observed in neural nets. And acceleration, actually, you can prove that acceleration is effective despite the sort of infinite condition number of this problems. Okay, so first I kind of repeating what Nat already said, but let me just very quickly repeat it. Computation is key. FARM, so the empirical risk minimizer, is found algorithmically. These algorithms are very important. And what do we need for large data? First, we have to map to fast GPUs, basically. Well, we don't have to, but it's extremely desirable to map to GPU. What can a GPU do? It can do matrix vector products, and that really limits the kind of algorithms which are available. So we have to look at the space of algorithms which are sort of mostly matrix vector products, not entirely, but to a large degree. And the large size of the data actually limits the number of this product that we can take. Now, so that's kind of a summary. What's the ERM algorithmic requirements? Kind of we want a small number of matrix vector products, and that's about it. All right. Now, what is this kernel architecture? So I'm kind of thinking of this as shallow kernel learning. By shallow, I mean you can view it as a two-layer neural net if you want. You map from your original space to some infinite dimensional, finite or infinite, but I'll think about Hilbert space, infinite dimensional space, and then I do some sort of regression or classification, some linear thing in that space, using maybe a square loss or some other loss. Now, for kernel methods, RKHS is all, well, for most interesting kernels, it's infinite dimension. And sort of a typical thing would be to think about a Gaussian kernel. And then you know, so if, I think most people are familiar, but if you're not, basically what you have a classifier, which is a linear combination of those kernels supported on your data point. So you have a bunch of, say, if your kernel is Gaussian, which is a very typical kernel, you have a linear combination of Gaussians. That's the output. And then you use that for classification or for regression. Now, OK, well, there is a long mathematical theory and statistical theory for kernels from, like splines and kernels machines and so on. What people observed is that they perform well on small data, not as well on large data. They perform OK, and they can be scaled, but they seem to consistently underperform. And there was some argument that maybe there is some sort of intrinsic architectural limitation because it's a shallow network. But it appears that a lot of this underperformance actually relates to the fact that if you take standard methods and you map them onto the GPU in an obvious way, what you get is algorithmically rather suboptimal, meaning that with a fixed computational budget, it's very difficult to actually fit arbitrary functions, or functions that you want to fit. And once you address this computational reach, you get pretty major speed and accuracy improvements. OK, so let me just point out what the problem is. Basically, if you just think about the square loss, then solving this kernel machine requires you inverting a large matrix. It's equivalent to solving a linear system of equations, k alpha star equals y. So you need to invert direct inversions and cube. Now, direct inversions, of course, is not possible on large data, like 10 million data points. You need 10 to the 21 operation. That's not possible. Now, you can do reiterative, which is gradient descent, or it's known as Richardson iteration, Landweber. There are a bunch of names for this. And this is nice. This is n squared per iteration, and much cheaper if you use gradient descent, stochastic gradient descent. It's GPU compatible. However, how many iterations do you need, right? That question was asked before. Well, let me give you an example. Consider Heaviside function. So you can kind of think of a very simple classification function. You have +1 here, -1 here, in just one dimension. This is what happens after 100 iterations with a Gaussian kernel. Now let me do 1 million iteration. OK, that's 1 million iteration. Well, can you tell the difference? Not very much, right? Almost the same thing. You didn't even get one in L2 loss. You didn't even get 1 bit of precision after 1 million of iterations, right? That's pretty disheartening. So nothing happens after 1 million iterations, basically. So you can imagine that to get any good precision would require you, too many. More than the life of the universe, probably. Now, you can see that on real data sets, there are some subsets of some standard data sets. You can just do this and see how many iterations you actually need. You see that you get complexity, which is at least cubic or worse. So it's worse than the direct method. These are small data sets, small subsets. So I can actually do the direct method. So I can pay in cube. For large data set, that would not be possible. OK. Now, let me point out now the limits of kernel. And here is a theorem. And I have to say that sort of the methods we use, we really use approximation theory with what those guys, approximation theory guys, developed. I don't have time to explain, but it's pretty nice. Here is so suppose I have a kernel operator. You can think of this as a kernel matrix. So what's a kernel matrix? I have a bunch of points. I have my Gaussian, right? So for every pair of points, you have a kernel, k of xi xj. So that's n by n matrix. The size of that matrix is equal to the number of points. What about eigenvalues of this matrix? Well, so you can prove that there are some constants C and C prime, which is kind of, well, not universal. They depend on the kernel, but they don't depend on anything else. They don't depend on this measure, for example, such that lambda I of k is less than something times an exponent in I. It's a little bit better than exponent, but I call it nearly exponential. Now, this actually gives a uniform bound for all kernel matrices. So that shows that the small eigenvalues of these kernels must be very small. Well, if you actually do this in one dimension, so generate some uniform points in one dimension, just construct the kernel, run it in MATLAB, you will see that almost all eigenvalues, so say you have 1,000 points, you will see that 900 of them are numerically 0. It's really very close to 0. These kernels are highly degenerate. So this is what I kind of call approximation beats concentration. If you think about those points and being randomly sampled, you would think that there is some bound of the 1 over square root of n type. But there is something much tighter here is going on, right? You actually have some sort of exponential convergence to 0, which is not easily suggested by, maybe you can get something like that from concentration, but it's not clear how you would get this. And also, this doesn't depend on the fact that they're randomly sampled. It just depends on the nature of the kernel. OK, now theorem 2, and basically say, well, let me now, I don't need a square loss for this one. Let me just run my gradient descent for a while after t step. What kind of VC dimension of functions can I reach after t steps of gradient descent? It turns out it's polylogarithmic in the number of steps. So that rather limits the fitting capacity of my kernel. For example, random labels are pretty difficult to actually fit using this. OK, now, well, you can see this actual eigenvalue decay. They are not quite exponential, but this is only like a 1,000 out of 10,000, and they are like, you have like 4 orders of magnitude difference between the largest and the smallest. So if you look further down, you kind of lose numerical accuracy, but you can see that like last few thousands of them are probably actually numerically 0, as far as you can compute in the machine. OK, so here is the kind of theorem. Only very smooth, well, there are some conditions here, but I'm going to skip that. Only very smooth functions can be epsilon approximated by a smooth kernel. And basically, you need some sort of exponential number of iterations of gradient descent if your function is not very smooth. That seems to contradict to the classical one of epsilon squared rate. It doesn't, because somehow in the infinite dimensional space, the norm of the solution is infinite. If you remember the bound, there is like norm of W star somewhere there, and this norm is actually infinite. So in every fixed dimension, it's true, but it's huge. It's gigantic. And if your dimension goes to infinity as you sample more point, you actually converging to infinity. So in infinite dimensional, things get tricky because these kernels, even though they're strictly positive definite, but they're extremely poorly conditioned. So OK, let me kind of address what. So this is what's wrong with them. Basically, the classification functions are not smooth enough to be approximated by kernels. Now, what is happening here? So I need basically exponential number of iterations to fit these directions. And these directions are important. So for the Heaviside case, you can actually analyze it. It's pretty easy. You see that you have linear decay of coefficients for the Heaviside function in the Fourier basis and exponential for the kernel. That's a big mismatch. Now, what do I do? Let me just tell you what sort of our solution is. I mean, certainly there could be others, but this is one way to do it. Well, suppose my original kernel is something like this. This is a spectral theorem for it. I write it in the basis of eigenfunctions. My problem is that these eigenvalues are kind of decaying too quickly. Well, let me just kind of flatten them. I can manually flatten them. So I construct this new kernel, modified kernel. The first k eigenvalues of this are equal to the k plus 1's eigenvalue of that one. OK, so you can kind of pictorially view this as the original kernel. This is a modified kernel. Now, this kernel is much nicer from the, actually, it corresponds to the same RKHS. The reproducing kernel Hilbert space is identical to the old one. But from the optimization point of view, this is much better because, well, first E1 to EK, you can see, it's easy to see. You just fit in one iteration. And then you have some constant but exponentially large acceleration for each next one. So that will converge much faster. Of course, so this is kind of a cartoon of this. This is all functions. This is functions which, gradient descent gets after t iteration. And this is what we get after t iteration if you could actually construct this kernel. And you can see it's kind of like taking an exponentially large step of gradient descent. Now, OK, well, you can say, well, OK, great. But I didn't tell you, OK, it's exponentially increased reach per step. But how expensive is each step? Right? Maybe step costs you exponentially more. So the nice thing is that you can actually construct something which approximates that kernel relatively cheaply. And the way to construct it, you build this preconditioner. You basically take these eigenvectors and you kind of rescale this manually. And the nice thing, using, say, Nystrom or RSVD, you can think about Nystrom, whatever this you prefer. You take a small subsample, you compute those things approximately, you expand them, and then you rescale this kernel using that. Nice thing about this, precondition is formed only once, and it's formed cheaply even though it's a kind of cubic operation, but it's a cubic operation on a small subsample of my data. By the way, notice there is no regularization. Regularization is very bad because I have so many small eigenvalues that I really should put all my effort into keeping some of them alive. Like any ridge, for example, would kill them or kill things which are valuable. OK, now, so this is basically you get this kind of preconditioned gradient descent, if you wish to call it, or preconditioned Richardson iteration, whatever you like to call the thing. And basically, it's low initial cost and kind of low overhead per iteration because of the way it's formed. You have maybe 15 or 20% in practice. And the nice thing is it converges to the exact correct solution for any p. So even if you misestimate p a little bit, it's OK. You will just sacrifice a little bit of your speed of convergence. OK. Let me skip the stochastic. We have some result for stochastic gradient descent. And in practice, you always use it with stochastic gradient descent. But I'll talk about this more. Let me show you some results. So this is a kind of acceleration. Basically, you get about 6 to 30 times acceleration factor using this. And if you think about actually overhead, it's probably like about 5 to 30 more realistically. But once you try them on some of the big problems which people have tried, you see that you consistently get better results. You get better or the same kind of results. So I don't know, 0.72 and 0.7% are not really that different. But you get it with much, much less computational power. So you get like 4 hours of GPU versus something like 1 hour on 1,300 CPUs. So it's much cheaper. And in fact, we kind of can beat every result in the literature. There is one which actually using some sort of learned features. So it's not exactly the same kernel. They do some clever kernel learning. But the nice thing that they report, for example, a result for deep neural network, well, it's a fully connected one. And the result we get is significantly better with just plain vanilla Gaussian kernel. Nothing fancy here, but with the preconditioning, of course. So we get better performance with much, much less computational budget. OK, so that's kind of how to address it. Now let me tell you something about this modern behaviors of kernel. And let me first tell you something about why SGD is so effective, why I think it's so effective in any case. And I think the major innovation here is this is joint work, by the way, with Siyuan Ma and Raif Basili. And I think the major modern sort of innovation is systematic overfitting. So it's not a new thing. People have noticed this for other boosts. And in fact, Peter had a slide from NIPS 20 years ago, which was exactly about this type of situation. But I think now it's extremely systematic. And the number of parameters is much larger than the training data, consistently huge. So this is a graph. This is a different architecture. This is some sort of summary from this paper. And the size of the circle is the number of parameters. It varies from the one I showed in the beginning, Google Net, is about 5 to 10 million. This is like 150 million. So it's 150 million parameters that you have there. All of them are like super, super rich families of functions. And in fact, OK, I'm not going to read this, but basically this is from Russ's Simon's tutorial like here 8 months ago. And he basically says, well, we always should overfit. You can read the quote. basically, let's turn off regularization, then overfit, then maybe we turn off it on a little bit and improve the result slightly. OK. So here is the thing. Overparameterization actually leads to interpolation. And what do I mean by interpolation? I mean that whenever you overparameterize, you basically tend to converge to a global minimum. At a global minimum, my function value is exactly yi. So f of xi is equal to yi. There is significant recent evidence that this kind of method find global minima for different type of architectures. I'm probably forgetting about some work of people in this room, so I apologize for that. Huh?
What do you mean?
Huh? What do I mean by what?
I mean, you just said that the local minima have zero loss, right? Is that what you mean?
All local minima have zero loss, and therefore they're global minima. It's not terribly surprising, because think about it. The number of parameters is so much larger than the number of actual. So think about local minima, right? At the local minima, all my gradients in every direction have to be 0. But there are many more directions, and they're actually constrained, which are data points. So it's not terribly surprising that in such when the number of variables is so much larger, then there is one direction which goes down. Of course, it cannot go down below 0 because I conspired, like my loss function actually conspired to stop it at 0. It's a sum of squares, or sum of some positive function. So, OK. So if you kind of believe that, then overparameterization must lead to to interpolation. And there are certainly, for specific types of functions, there are theoretical results for networks. So now there are two questions. Why are large models so easy to optimize? And why do large models perform well? So easy to optimize, I'll say something about this in a second. But why do they perform well? I think it's a total mystery, because it does contradict classical generalization results. And, not classical, most of any generalization results, really. And if you see, actually, this is from the Rethinking generalization paper, you see it doesn't really matter what you do, your train accuracy is 100%. So L2 loss is actually not reported here, but you can see it's very close to 0. So there is a big gap between train accuracy and test accuracy. And there is no bound of this form which could sort of reasonably bound that.
For every term there, I can find a C such that it's true.
A C.
You have a C.
Yeah, but it's not interesting, right? Sure. I mean, take C to be 10 to the 100.
No,
Here we go.
I could actually back solve for what C should be.
OK. Yeah. I'm saying there is no systematic bound of this form, which actually can give us some sort of consistent and interesting result in this mode. Not to say this bound never correct.
I was kind of joking, but I want to push back on this. What do you mean that this is not consistent? That these results are not consistent with the 1 over square?
No, these results are correct. They're mathematical truth. But they don't explain what we're seeing.
That's what I would like you to explain more carefully.
So, OK, let me just say one thing. Think about one nearest neighbor classifier. One nearest neighbor classifier gives you 0 error on your training loss. It gives twice the base error in some limit appropriately on the test. But there is no result of this form which can kind of increase it for 1, 0. You need some other analysis which you kind of use for 1, 0, one nearest neighbor classifier. So I think here something like that is happening. But I'm happy to talk more about that because I'm sort of short on time. And this is a long discussion.
I understand that you're short on time. I just want to understand what you're saying because it's very interesting. What you're saying is that you feel like this might actually be asymptoting and not going to 0 because the data set is so large?
I think what we see is that they always take 150 million parameters. So the number of parameters is always so much larger. We're effectively in this asymptotic regime. We are not taking the training data to infinity. We are taking the number of parameters to infinity.
That perhaps this is base error here and something weird is happening.
Some function of the base error or something. Yeah. OK. So I don't think margins, well, so that's basically my point. So I'll show a very parallel result for kernels. So it's clearly not something special to neural networks. But let me let me just say a few words about why SGD works so well. Actually, this is very interesting because I think, so in general, SGD is kind of, so SGD you just do one term at a time, basically, or some small number of terms at a time when you do SGD, right? In general, it's kind of hard to analyze because you can kind of increase one loss function but decrease the other one. So there is some sort of, you have to play with like averaging and so on. However, there is a special case, and in fact it's observed. I think Moulin and Bach was the first paper which observed it. There is some sort of exponential regime for that. And in fact, Nati's paper was also says this explicitly. It's in Rachel, yeah. What happens is that when each of the small losses function is 0, you get exponential convergence. And that's exactly what happens in the overparameterized regime, right? We have each one of those guys is 0, almost all of them are 0, I don't know. And so we have exponential convergence, so that's why it's kind of like a regional perceptron. Why does it converge quickly? Because somehow the final loss is 0 when in the linearly separable case. If it's not linearly separable, it will oscillate. Okay, now we can actually improve on this result because, well, just exponential convergence is not enough because you have to compare it with full gradient descent and you have to look at the computational requirements. And this is a little bit, well, it involves a little bit of work. Kind of elementary, but sort of requires a little bit of work. But it actually turns out that gradient descent of size 1 is computationally optimal. So it's always best in a parallel, in a sequential machine. You take m. It's always better to take m steps of one gradient descent than take a mini batch of size m. However, there is some linear scaling here which is quite interesting. Basically up to trace h. So this is for quadratic or near quadratic loss, near kind of minimum when you can approximate it with a quadratic. You have trace h divided by lambda 1 of h. And up to that point, you're basically scaling linearly. That means that if you have a parallel machine, you are very good in this regime. You are getting something for free. Beyond that, you get saturation. And after that, basically, even if you put infinitely many processors, you compute full gradient descent, you only get a factor maybe of 2 or some fixed factor beyond that. And it's very consistent with what people actually observe empirically in neural nets. They call it linear scaling rule, but they can kind of increase the step size of gradient descent more than you would think. But it's very consistent with the regime where you actually have this, the loss is 0. Each of the small losses is 0. In fact, what they do some warming. So I think they call it pre-warming or something, and that basically kind of gets you in the neighborhood of that, and then they increase the step size, and that basically I think that's what we think. You can basically look at kernels, see that what you get in kernels is very consistent with this again, up to some small constant. Okay, let me skip this. Now let me talk about overfitting. What is overfitting? Overfitting is this. This is when your train error is 0, right? So I'm running my, so this is this accelerated Eigenpro. And I'm running this more and more epochs, kind of like what Nati was showing before. And you basically have 0 loss. You can see that L2 loss is also very small. It's like 3 times 10 to the minus 5. So it's pretty close to 0. So I'm literally interpolating here, at least in this kind of numbers. And you can see that the test doesn't change at all. 1.23, 1.20, 1.20, 1.23, okay, I don't know. If the difference between 1.20% and 1.23%, maybe, it's unclear. And so this is kind of interpolation. This you can say overfitting, but it performs really well. Now actually, here is the point. It's kind of hard to observe using standard methods, not because it doesn't happen. It actually does happen. It's just you need many more iterations, because even after 320 iterations, you are still kind of not, you're basically like here somewhere. So it's quite expensive to observe using the standard gradient descent, but you can. But I think people have observed it less because the computational capacity required is nobody had the patience to run this long enough, basically. Especially without a GPU, like 5 years ago, GPUs were slower, so it was just much harder to observe. Well, this is not specific to MNI. This is a large data set, TIMIT. It's basically observed exactly the same thing. So at least we tried on a bunch of data sets. it's the same. So, okay, why do overfitted models perform so well? We don't know. However, clearly this is not something which is unique to deep architectures, and in fact, kind of boosting clearly shows that similar things have been observed for other things. And in fact, Peter pointed out that something like that was also observed for trees, right? For random forests. But now we can actually examine it in a convex analytical setting, so there is much more hope that we can do this. And in fact, it's interesting that Laplace kernel does seem to perform a lot like ReLU networks, and if you try to fit random labels, you actually have some very similar behavior there too. But let me skip that point. Okay, so that's that, and okay, I'm running out of time, but. Okay, let me just say one word about acceleration. You cannot quite use, so it's actually much clearer what acceleration does in the kernel case because it's just linear, and you can kind of see that this is some optimality properties of polynomials which you can analyze. But the condition number is actually infinite for the things, so classical analysis don't quite apply. But you can still prove things, so we have some results that basically that there is some provable acceleration. In fact, Chebyshev method is optimal, it seems. Not just for the classical case, but for this one. But I'm going to skip that point. Okay, so maybe I should conclude. Okay, so first, classical kernels, I think they can work as a convex method for modern ML. They do show similar performance, at least with respect to fully connected neural networks. It's unclear for. It seems that convolutional layers are doing something quite different, and that is probably essential. So we cannot understand it from this type of analysis. We probably need some other type of analysis for that. Once computation is addressed, we have comparative performance and this kind of modern behavior, whatever that means. Can we design kernel for computation? Now, SGD is actually very effective for overparameterized methods. So what I think what happened is that people realized that overparameterized methods, somehow you can optimize them very well. And by this magic, they just overfit and it's OK. There is some sort of confluence of luck there, a little bit maybe. I don't know. OK, why do they generalize? That's unclear. Infinite condition number everywhere. I think we actually need to think about infinite condition numbers because once you have your data and those data, once your dimension is high enough, empirically you can just compute. Even if you have like 100 points in dimension like 50, you probably have a lot of eigenvalues which are very small. For like 1,000,000 points in dimension 1,000,000, there are going to be so many of them close to zero. And finally, okay, well, so there is approximation clearly going on and optimization, but so what is the trade-off between them? For example, it's not clear to me how statistics, so there is a statistics of data, but how does it play off with all the things? I'll stop now.